All right, now we'll discuss a use of radioactivity, radioactive dating. I'm sure you've heard of that. So let's talk about carbon dating. So the isotope used for carbon dating is carbon-14. Carbon-14 has a half-life of 5730 years, 6,000 years. So the half-life is almost 6,000 years. Now, carbon-14 is made in our atmosphere all the time. So cosmic ray protons and muons react with gases in the atmosphere, and they produce carbon-14. So there it is, and it's always been going on, all right? So we always know there's being carbon-14 being produced in the atmosphere, which reaches us. Now, for a living organism, people have measured the ratio of carbon-14 to carbon-12. You know, carbon-12 is the most prevalent kind of carbon, right? Carbon-14 is the radioactive one. So people have measured this for years and years and years, and they get this number, right? So the ratio of carbon-14 to carbon-12 is pretty small, but it's easily measurable. Okay? Great. So let's discuss how this carbon dating works, all right? Okay. And again, here's the interesting things, right? Yeah. Okay. All right, here we go. The principle of, they call it radiocarbon dating here. Okay, so so carbon-14 is formed in the atmosphere, and it's incorporated into a living organism through the food chain, right? I mean, if it's in the atmosphere and, you know, it becomes part of the apples, when we eat the apples, we get the carbon-14. So, and we're going to call this Eve, all right? So Eve, okay? So Eve is eating the apple. Okay, so while Eve lives, she exhibits a mild, steady level of carbon-14 radioactivity. So these arrows indicate that she's radioactive. All right? Great. Now, B, at death, she no longer eats, so she no longer gets any more carbon-14. So at death, the carbon-14 uptake ceases. Okay? C, much later, there's Eve. Much later, the carbon-14 activity has decayed considerably, right? Because, you know, she's no longer taking it in, and so that carbon-14, it's decaying. And it's decaying slowly because it has a 6,000-year half-life, right? So, all right, so here, you know, there's a lot of radioactivity, a lot of arrows. Here, there's not so many arrows. This is just indicating that a lot of that carbon-14 has decayed away. Okay, D, archaeologists excavate the long dead remains. By measuring the carbon-14 activity, they can infer the time since death, right? I mean, if she were alive, this would be the ratio. But since she's been dead for however many thousands of years, this number will be less because the carbon-14 will be less. And since they know the half-life of carbon-14, they can figure out how long it's been since she died. Okay, one more thing. It says, note that the archaeologists, with their active carbon-14 intake, are much more radioactive than Eve, right? Because, you know, all the C14, not all, a lot of the C14 in Eve has decayed away. So they are super radioactive compared to Eve. So that's basically how you do it. Now, there's an assumption here, right? The assumption is that this has always been the same, right, over a long, long time, okay? Now, in fact, that's false because nuclear weapons testing produced additional carbon-14. However, people know how to take that into account. So this process or this procedure, carbon-14 dating, it really, really works well. And people use other isotopes to check it. And there's a great agreement, okay? Now, obviously, you're only going to use carbon-14 dating for very, very old objects because, you know, you want it to decay an appreciable amount of time. It has a half-life of like 6,000 years, so you're not going to use it for something that's, so you want to use it for only really, really old things. Okay, let's do another way of doing this. All right. Another method, and you should have your radiometric dating handout with you right now, because we're going to go over the handout. And this is the picture on your handout. So let's do it. All right. Okay, so it says, assume you have a large number of radioactive nuclei, and the half-life is the length of time it takes for half of the nuclei to decay. No kidding, we already know that. All right, so nuclear physicists have observed that potassium-40, so K40, decays to argon-40. All right? And we don't care about all the details. But we know that happens. And we have 1 gram of K40. Great. So here's it. Let's go over the questions. So after 1 half-life, how much K40? So how much K40 is there? Well, you started with 1 gram. It's a half-life, so half decays, right? So we have a half a gram. Okay. How much argon-40? Well, we started off with 1 gram of K40. Half of it decayed, it became argon, so half a gram. So half a gram. So therefore, what's the ratio? What's the ratio K40 to argon-40? What's the ratio? Well, it's a half divided by half, so it's 1. Or you can say 1 to 1, whatever you like. All right. How about after 2 half-lives? Okay. How much K40 are you going to have now? Well, here we had a half. We have another half, so a half of a half is a fourth. So we have a fourth of a gram. Okay, argon-40. We had a half, but now we have another fourth, right? Because the potassium decayed into argon. So 1/2 plus 1/4 is 3/4. So we have 3/4 of a gram. And what's the ratio? So the ratio K40 to argon-40 is 1/4 over 3/4. And what's that? It's a third, right? It's a third. It's a third, okay? A third. All right. Okay, last one. After 3 half-lives. Okay, so the K40, so what's half of a fourth? An eighth of a gram. And argon-40. So we had 3/4, which is 6/8. Then we get another 8, so we have 7/8. 7/8 of a gram. So the ratio K40 to argon-40 is 1/8 divided by 7/8. And that's what? 1/7. 1/7, which is 0.143. All right. So this ratio, what does it depend on? What does that ratio depend on? It depends on the elapsed time, right? After 1 half-life, the ratio is 1. After 2 half-lives, the ratio is 0.333. After 3 half-lives, it's 0.143. Okay, so the ratio depends on the elapsed time. All right, now we got to kind of keep that around. Oh boy. So this is 1 half-life. This is 2 half-lives. This is 3 half-lives. Okay, you find a meteorite on the beach. Chemical analysis reveals that the meteorite contains 3.2 micrograms of K40 and 22 micrograms of argon-40. And we know that the half-life of K40 is about, well, let's just say equals 1.27 billion years. All right. So how old is the meteorite? Well, come on. The ratio of K to argon gives you the elapsed time. So we have the amount of potassium, we have the amount of argon, so what are we going to do? We're going to find the ratio, right? So the K40 to argon 40 ratio is 3.2 micrograms divided by 22 micrograms. And I promise you that is 0.145. Wow! What does that indicate? How much time has elapsed? One half-life? No. 2 half-lives? No. 3 half-lives? Yeah, right, or close. We're just doing approximately. So this ratio is 0.145. After 3 half-lives, the ratio is 0.143. That's approximately the same. So what we're going to say then, we're going to say 3 half-lives has elapsed, right? Okay? So, awesome. So now we know that the half-life is 1.27 years, so we say 3 times 1.27 billion years. And when you do that, you get 3.81 billion years. Okay? So that means that the meteorite is about 3.81 billion years old. Question number 2. In order to answer the previous question, you had to make an important assumption concerning the meteorite. What is it? All right, so what are we assuming here? You know, we're assuming that we didn't have any argon to start with, right? I mean, right? We're assuming that the only way we get argon is from the decay of the potassium. Now, is that a good assumption? Well, yeah. I mean, argon is a noble gas. It doesn't react with things. It's not going to be found in a meteorite. So it's a good assumption, okay? So there you go. This is another great way of dating something. All right. Okay, so basically what people do in the real world, they use more than one method, and they compare the answers. And they agree, right? That's why people use this. Radioactive dating, that's how people figure out the age of the solar system and all sorts of things. So that's pretty useful. All right. Right at the beginning of this chapter, we said that we were going to come up with a model of the nucleus. You know, when we did the previous chapter, we had, you know, the infinite potential well. Remember that? And that was just a model, right? That said that the neutrons and the protons don't interact at all and they can't escape. Now it's just a model, but it certainly wasn't a great model because number one, we know that the protons and neutrons interact with a strong force. Number two, it's not an infinite well, right? I mean, there's radioactivity. Things leave the nucleus, right? All right, but that was a good, you know, start, right? Good start. Well, now we're going to talk about the shell model, the nuclear shell model. And it's a big improvement over the infinite well. All right, but there's still some approximations, you know? All right, so what we're going to say is that every nucleon, either proton or neutron, moves independently, but there's an average potential energy due to the attractive nuclear strong force, right? Okay, so we're saying we have all these nucleons, you know, there's this attractive nuclear force, strong nuclear force, and so here it is, okay? So the average neutron potential energy is due to the strong force. Okay, now it's an attractive force. So we're going to say, all right, so the nuclear strong force, it's attractive. So like we had in the past, we can say that U is less than 0 for attractive, okay? And so here it is for the neutron, all right? So you can see that it's negative, right? So we have this negative well, all right? And And it's finite, agree? It's not infinite, it's finite, okay? So there it is for neutrons. So what we're saying is that's all they have, right? They just feel the nuclear strong force. That's it. All right, fine. All right, well, how about that's neutrons, well, how about the protons, right? Now the protons, much more complicated, right? So the protons, more complicated, so they still have this nuclear strong attractive force, but what else do they do, though? Protons repel protons, right? And, sorry, I know, for the people who haven't had Physics 220, the force is proportional to the distance squared, okay? So you have the attractive potential energy due to the attractive nuclear strong force, but then, okay, so this was all right, so the force is proportional to 1 over r squared. The potential energy, we learned in Physics 220, is proportional to 1 over r, all right? And that's repulsive, right? So you have this attractive thing here from the nuclear strong force, then you have this 1 over r, the potential energy due to the other protons, okay? So it's more complicated, right? There's two pieces. So the average proton potential energy is due to the strong force, attractive, and the electric force, repulsive, right? And this is the potential well depth for Z is about 30. Okay. And you can, again, this is negative, right? This is negative due to the strong force. This is negative due to the strong force. But this is positive, right, due to the repulsive. So that's why, here you just have negative. Here you have negative plus positive. So that's why this is minus 50, this is minus 35, right? This gets booted up because of the positive repulsive force. Okay? Okay, now, sorry, we have to learn something that we haven't talked about yet. So in chapter 41, we're going to talk about the Pauli principle. All right, the Pauli principle. And it basically says, and you'll understand this later, don't worry about it. So no two fermions can have the same quantum number. Can have the same quantum number. So you say, what in the world is that all about? Well, we're going to see next chapter that every particle has certain quantum numbers, masses, momentum, angular momentum, so energy, stuff like that. Okay? So don't get all excited about that right now. But what this means is that this restricts the number of electrons in each state. So it restricts the number of electrons in each quantum state. And, okay? And so we talked about filling a shell. You probably learned this in a chemistry class. Now, what's a fermion? A fermion is a spin half particle. So it's a spin half particle. So it's a proton and a neutron, okay? So protons and neutrons are spin half particles. And so is an electron. So protons, neutrons, electrons. Okay. All right, here we go. So let's talk about this. Let's give an example. All right, so we're going to do the easy case first and then the more difficult case later. So let's do nuclei where Z is less than 8. Okay, so the number of protons, which is, is less than 8. Well, here, if there's hardly any protons, the electric potential energy is really, really small compared to the potential energy due to the strong force, all right? And so we're going to ignore it, all right? We're going to ignore it. So basically, we're going to say that the potential energy well for the neutron is exactly equal to the potential energy well for the proton, right? We don't care about that repulsive electrical force. It's small. We can ignore it, all right? There's not enough protons to get excited about. Okay, so here we go. We're going to look at this in gory detail. So this is that potential energy in MeV. Okay, so these are the energy. Okay, so these are like the quantum states. All right, the quantum states. And this is the number of nucleons allowed in each quantum state. You don't have to understand it. Just take it. Just take it. All right. So in the n equals 1 state, you can only have 2 nucleons. N equals 2 state, you can have 4. N equals 3, you can have 2, and so forth and so on, all right? So these are the first 3 allowed energy levels. They are spaced several MeV apart, right? MeV, not EV like in chemistry. Okay, these are the maximum number of nucleons allowed by the Pauli principle. I said that. The neutron radial distance is measured to the left. The proton potential energy is nearly identical. Yeah, I already said that. Okay. Great. All right. So let's use this. Let's use it. So let's consider carbon-12. Now this will make sense. All right. Okay. So carbon-12 has 6 protons, 12 nucleons. Well, 6 of those are protons, so the other 6 has to be neutrons, right? Okay, so there's 6 protons, and 6 neutrons. Now remember, you can only have 2 nucleons in this state. You can have 4 in this state. By the way, the up and down is a spin that we'll talk about next chapter. If you have to have different spins. So this is spin up, spin down. Okay. All right. So look. So the max is 2. We got it. The max is 4. We got it. So in other words, it's kind of like in chemistry. We're filling the shells, right? You can only, at most you can have 4. We got it. At most you can have 2. We got it, right? So everything is full. So that means it's going to be super stable, all right? It's tightly bound, high binding energy, all right? Okay, let's do some other ones. Let's do helium. Let's do helium. Let's do helium-4. All right. So draw the same picture. I'm not going to be so nice about it though. So here's 2 and here's 4. This is the protons. This is the neutrons. All right. So we have 2 protons. So 1, 2. We have 2 neutrons. So 1, 2. Bingo. So they're full, right? They're full. So you'd expect helium to have a high binding energy. Highly stable. Let's do oxygen 16. Proton, neutron. Okay, so we have 8 protons. So 1, 2, 3, 4, 5, 6, 7, 8. We have 8 neutrons. So 1, same thing, right? All right, so what do you say? Once again, everything is full. So super stable, high binding energy, on and on and on. All right? So, you know, carbon-12, highly stable. Helium-4, highly stable. Oxygen-16, highly stable. Now, where have we heard that before? Remember that? A while ago? This was the binding energy per nucleon, and we saw that helium was super high binding energy, carbon-12, high binding energy, oxygen-16, high binding energy. Well, that's why, okay? Because all their shells are full, okay? On the other hand, let's do one that's not the case. In other words, their shells are not full. So let's do this guy. Ooh. All right. So now this is where you have to do it. So pause your video and draw a graph for, was it boron 12? So, all right. So you have to get used to doing this. So pause your video and draw it. All right. So I assume you've done it. Okay. So 1, 2, 3, 4, 5. So we're not full, right? Because a 4 would be full. And then there's 7 neutrons. 1, 2, full. 3, 4, 5, 6, full. 7. Okay, so this is missing one. This has one additional one, right? Okay, so look, you know, we want things to be, I mean, nature wants things to be stable, right? Well, this is not stable. We have one extra neutron, one missing proton. To be stable, right? I mean, if this was over there, it'd be super stable. So, how can we make this thing stable? So you have this boron 12, you know, radioactive nucleus. It wants to become stable, right? It wants to get rid of some of this excess energy. It wants to be stable. How can it do it? What do you think? Well, all we have to do is put this neutron into there. Well, what do you mean you put a neutron? So the neutron has to be converted into a proton, right? That's what has to happen. Neutron become a proton. Now, how does that happen? Well, we already talked about it, I think. Yeah, we did. All right, we already talked about this. This is just that this was what we saw in the P221 decay, right? So the neutron becomes a proton, and then an electron and an antineutrino and some energy given off. Okay? So a boron 12 nucleus could lower its energy, become happier, stable, if a neutron could turn into a proton. Okay? So, does this happen? Yes, it does. We saw this. This is just beta. This is a beta radioactivity, right? And so, you know, it happens. So let's look at boron. There's boron 12. Wow, what is it? It's a beta emitter. Woohoo! Look at the half-life, 20.2 milliseconds. So it happens all the time, okay? All the time. Let's do another one. So you pause your video and draw the similar graph for nitrogen 12. So please do it. All right, so I assume you've done it. Okay, so 7 protons, 1, 2, 3, 4, 5, 6, 7. 5 neutrons, 1, 2, 3, 4, 5. We're missing one here. We have an extra one here. You know, we want to have 2. We don't have 2. So how could this thing become more stable? Well, if the proton became a neutron, right? All right, well, how do you do that? Well, piece of cake. It's called beta plus radioactivity. So you have the proton, so there's a +1 charge, so you have to have a +1 charge over here, all right? So the proton becomes a neutron, and there's a beta plus, right? It has to be a positive, because you have a positive charge here, you got to conserve charge, so you have to have a positive. This has 0, this has 0, so you have to have a beta plus, okay? There you go. So, does that happen? Oh, look at that. Nitrogen 12, beta plus, 11 milliseconds is the half-life. Amazing, right? All right. Now, but here's a very important question. Which particle has the greater mass, proton or neutron? We just saw that a little while ago. The neutron has the greater mass, right? So how is this thing going to happen? All right? This is not a spontaneous decay, all right? If you have the proton just sitting there, this is not going to happen. The only way that this is going to happen is if somehow this proton has like extra energy, okay? So this proton has to be energetic because this mass is greater than that mass. So it's not spontaneous. All righty, that's a good place to quit.